All right. So this is the R Greater Cleveland R user group. I'm Jim Hester. I'm one of the co-organizers of the group, along with Tim Houlihan, and I'll also be the speaker today. So just wanted to mention our talk for next week is by Mukul Mehta, who's here. He's going to be talking about using R Markdown and Shiny with teaching R&D chemists. So that's actually pretty interesting. I'm looking forward to that talk. I think it's an interesting use case. So hopefully everybody can attend that. And we currently don't have a speaker we have a joint November-December meeting at the beginning of December, just to avoid all the holidays. So if you're interested in giving a talk, we'd love to hear it. It doesn't have to be like it could be what you do at your work with R and how sort of challenges you come up with and things like that. It doesn't necessarily have to be a full project or anything like that. So whatever if you want to workshop a talk or just get some practice in front of a live audience, this is a really good audience for that. So if you have any ideas, I'd love to hear them afterwards. The meetup group is sponsored by a couple different people. Our studio gives us a little bit of money. The R Consortium also, the Microsoft and the Revolution Analytics brand, and Level 7 lets us donate the space. So just to talk a little bit about myself first. I'm actually gonna go back one. So I'm currently a software engineer at RStudio. I have been there about 3.5 years, and I work remotely. RStudio is a distributed company, so most of the company we're actually based out of Boston, but most of the company doesn't work there. And I still, after 3.5 years, have yet to go to our office, so which is unfortunately ending in next month. So I'm sad that my streak is ending, but that's okay. So like I said, I've been there for 3.5 years. I work on the Tidyverse team during developing the Tidyverse R packages, the open source R packages. Before that, I worked on the bioconductor core team for about a year. Then I was also a data scientist at a healthcare startup in Cleveland called Exploratory. And before that, I worked at the Cleveland Clinic as a program analyst and doing bioinformatics in the Learner Research Institute. Which brings me, we actually just yesterday launched a new version of rstudio.com. So if you haven't been there in a while, it's a good time to check it out. There's some really nice resources now for free resources on learning R. We have all of our what we do monthly, I think, webinars, and all of the webinars are online. There's the cheat sheets. There's links to all books that RStudio employees have written, many of which have online versions for free. There's some more things about in-person workshops that might be running and other things like that. So I really encourage you to check it out. And another new site is the education.rstudio.com, which has really good resources specifically for people new to R or learning R, and actually various levels. So there's a whole page on beginning resources. There's an intermediate page for intermediate resources and advanced resources. So it's really good, and they're not all resources done by RStudio. It's just sort of a collection of good free links for everyone. So I really encourage you to check it out. And finally, I recently redid jimhester.com, so it has all of my talks, all of the talks that have been recorded, my projects, any blog posts, and I've also done a few YouTube videos on live coding various things. So if you want to know all about me, that's where you go, jimhester.com. Okay, so that's enough advertisement. So what am I going to talk about today is the vroom package, because life is too short to read slow. And the slides for this package are on SpeakerDeck, speakerdeck.com/JimHester/vroom. So if you want to reference them later, that's the best place. So why did I write this package? So when you're developing a software system, there's I think 3 different thresholds you need to keep in mind when you're trying to develop it. In particular, a software system that users are going to be interacting with in real time. The first threshold is a tenth of a second. So in that threshold, users perceive that as basically instantaneous. So they perceive it as the computer just reacting instantly to whatever actions they're telling it to do. Thresholds around a second are no longer instantaneous. The user can perceive that something is happening, but they're still fast enough that the user doesn't context switch and to do something else. And then once you get to about 10 seconds, it's too long, the user gets bored and goes and does whatever else. So another way to phrase this is that you need to design your interactive programming environment so that they give you feedback faster than your impulse to open Twitter or Hacker News. You're really always fighting the user impulse to go do something else. So I'm going to be showing a bunch of benchmarks in this example, and I wanted to explain what the data set I'm using in these benchmarks. This data set is a real-world data set of taxi trip fares. And it has about 15 million observations, 11 variables, a file size of about 1.5 gigabytes. So this is not like an astronomical data set. This is something you can actually analyze on like my laptop, but it's fairly large. And it has a couple different data types. It has a few character columns, such as so these are taxi trip fares. So each row in the data set is one taxi trip in New York City. So there's the medallion, which is the taxi medallion that the taxi is using, the license, and a few more things. There's a few double values, such as the price of the fare, the surcharge, and other things. And there's also one date time. So that's when the taxi was when the trip started, basically, the pickup date time. So what does it look like when you read this data set? So the first thing you should look at is this top column is using read.delim. So this is the function that's built into base R. You don't have to install any packages to use this. And that function for this data set, takes around 80 seconds to run, to read in all of the data. And then I showed a couple more packages, so popular packages for reading and data. So the readr package, which I'm actually also the maintainer of readr. Yes?
What is the file type of the data?
Oh, so it's actually, I'm trying to remember what I used for the benchmark. So it's a CSV, the raw data is CSV, but I don't remember exactly if I read it in these benchmarks as a CSV or if I converted it to TSV and then read it that way. But it's essentially the same either way. It's either a CSV or a TSV. So it's separated by commas or tabs. That was a good question. And I should say we're a small enough audience. Just interrupt me at any time if you have questions. So the readr package is, like I said, it's the package in the tidyverse suite of packages that is used for reading and data. And it can read CSV, TSVs, fixed width files, and a few other formats. Data.table also has in addition to all of the data.table functions for doing data manipulations, it has a fast function called fread for doing reading and delimited files like CSVs and TSVs. And so that's the other package that I'm showing in this benchmark. And then vroom is at the bottom. So vroom is able to read this. So going from 80 seconds, it's able to read this file in 1.8 seconds. So that's a huge improvement. And that really gets us into that threshold of between 1 and 10 seconds that we're really aiming for, where the results maybe not are completely instantaneous, but they're fast enough you don't context switch and do something else. So how are we able to read this file so quickly? What are the main drivers of our engine here? So the first thing is, and these are listed in sort of least to most important, is that we're using memory mapped files. So memory mapping is an operating system primitive that lets you interact with a file as if it was as part of your RAM. So the OS really handles like the paging of the file. The next thing that the vroom does is it's multi-threaded, so it's taking advantage of all the cores in your machine. Thirdly, it uses this efficient C function called string compare span. And this function is part of the standard library of C. And it's often implemented in handwritten assembly, so it's very efficient. And this is actually the function that's used to find all the delimiters and also quoting characters and a few other things. So we're taking advantage of this very fast C function for the tight loop of when we're parsing the file. And finally, and most importantly, we use this new thing in R 3.5 called Altrep, which I will go into. Yes?
What were the specs of the machine you used? Since you said small,
Oh,
right?
yeah, so it's this actually this laptop. So it has like, well, it has four hardware cores and so a total of 8, and it uses hyper-threading, like Intel hyper-threading, so it has a total of sort of 8 processors. Let's see what else. I can look at the.
16, 32, 64, 9.
Oh, so it has 16 gigabytes of RAM. Let's just look. I don't know. I can't unfortunately make this bigger. But it's 2.5 gigahertz Intel Core i7. Yeah, 16 gigabytes of RAM. I mean, it's like from 2015, so it's like it's okay, but it's nothing like terribly impressive. You should get like around the same performance as long. So the sort of the most important performance thing in this case is actually it's actually having an SSD hard drive. So the hard drive access is really fast. So that's probably like when you're doing this reading, it's really I/O bound for the most part. So having like an SSD hard drive is really useful, which this laptop does have. Okay, so what is this Altrep framework, and how is it beneficial for vroom? So it stands for Alternative Representation, and this was a framework introduced in R 3.5 and up. So if you're using any version after that, you'll have access to this. It's really something that's sort of in the underpinnings of R. It's not really something that users will even have to be aware of. But packages can take advantage of it as long as the users are running R 3.5 plus. And what this framework allows is custom memory storage. So by default, an R vector is sort of just a pointer with metadata and then a blob of memory behind it that is storing all of the data. And what Altrep lets you do is have the same blob of metadata, but then the blob of memory can be different. So it could be coming from like a database, or it could only be allocated like as needed. So that really what is in that blob of memory is customizable. And this framework is also transparent to users R and C and C++ code. So it doesn't matter what code you already have, it can take advantage of this Altrep framework without any changes on the user's part. And all of this features combine to allow us to use on-demand parsing in vroom. So what does on-demand parsing mean? That really basically means that when we're doing that initial read, all we're doing is finding where all the delimiters are in the file. We're not actually reading the values. We're not parsing all of the individual values at that point. We're only parsing the values when you use them later on in your analysis. So what is actually the difference between, what's the speed up we actually get with using this Altrep framework? So the top highlighted bar is vroom without using Altrep. And the bottom one that I showed before is vroom with using Altrep. So that's really a lot of the speed benefit we get over like data.table, for instance. So we're going from just a little under 20 seconds to less than 2 seconds. So why do we get this so what is slow that's causing this slower parsing without using Altrep. And really, a lot of it boils down to the global string pool. So R has a global string pool where all strings used in an R process are hashed and then put into this global string pool. So if you have a vector x up at the top here, and that's like, we'll say it's a character vector and it has 5 values, and these are actually the values in this character vector. So if you say x or you index the first index of x, that would be a. And so you might think that that a value would be stored in the vector directly, but what's actually stored in the character vector is just a pointer into this global string pool. And the benefit of that is that if you have another vector y, in this case y only has 1 value, but it's also a. So the actual bytes that store that a value don't have to be duplicated. All that's in y is a pointer into that global string pool. So this means that if you have a really long strings, that the data in the strings only, and you're repeating them a bunch of times in your program, like let's say in a data frame, you have a character vector that has a lot of repeated values in your entire data frame. Those repeated values aren't stored over and over again. Or even if you say you have 2 different data frames and they all have these repeated values, those values aren't stored again. You only store them once in your memory. So that's the real benefit of the global string pool, is that it uses much less memory for character data. But the downsides are we have this somewhat expensive hash lookup that we have to do. So we have to figure out, when we're creating a new character value, we have to figure out if that value is already in the global string pool. So we have to hash that value and then look it up in the global string pool to see if it's there. And so that takes some time. And then we also, because we have this global string pool, we have to do this in a single threaded way. So we can't take advantage of multiple threads in creating these character vectors. So these 2 things really make it give you a hard lower limit on how fast you can read data into R. So I mentioned that vroom has this lazy approach to parsing. So that has to come at some cost, right? Because if we are delaying parsing all of our values until later on, we can't, we eventually have to parse them at some point before we can use them. So what is actually the cost of this? So the benchmarks I was showing before aren't really a true representation of what we need to look at, because we have to actually do something with the data a little bit and then see how what our overall time ends up being. So that's what this is showing. So the light blue is the same benchmark I showed previously, and all of the colors are doing various operations on the data. So we're doing a few different things. We're printing the values, so these are reading into a data frame, and then we're printing the data frame. We're taking the head of the data frame, the tail of it. We're sampling a couple rows in between, in the middle of the data, and then we're also filtering by 1 column in the data, so based on the values in that 1 column. And then the last thing is the most expensive, is we're doing a group by and then a summation and aggregation of a different column. So we're grouping by 1 column and then aggregating. I think we're taking the mean of another column. And so if you look at this, even after doing all these operations, our total time still is much less than any of the other results. So this really shows the utility of using this approach, in that you can do a lot of, especially when you're doing these types of things, you're doing them interactively. So maybe you want to look at and see what the data looks like and then do a few things. Look at the first few rows, look at the last few rows, sample maybe within the rows, do some exploratory analysis of a column. And you can do all of this, and all of these intermediate steps all sort of fall within our 1 to 10 second threshold. So you're never having to context switch away because something is taking too long. And the other thing to mention is that the maximum cost that this will ever incur is basically the same as using vroom without Altrep at all. because once you've parsed all the values, it's essentially equivalent to reading the data eagerly and having all the values up front. Once they're parsed, as far as R is concerned, the data looks exactly the same as a normal vector. So the benchmarks I've been showing so far have just been using this real-world benchmark with a bunch of different data types. But it's useful to look at how vroom performance changes with all of one data type or another. And the two most important are double values and character values. So first I'll show benchmarks of just a data set of all double values. So this is a synthetic benchmark that just has 1 million rows and 25 columns of all just various double floating point values. And again, these are the same functions that we've been showing throughout. And in all of these benchmarks now, I'm doing all of the operations as well. So the first thing to note is that read.delim is extremely slow for parsing numeric values. So it takes 125 seconds to parse this data set using read.delim. So it's very slow. So if you're using read.delim, just use a different package, any package really, and it will be much, much faster. So I'm actually going to take it out and just look at the rest of the packages now. So all of these, if you look at the x-axis, all of these are reading this data set in under 5 seconds. So they're all very fast. Numeric data is pretty easy to parse, so it can be read, and it also doesn't have this problem with the global string pool. So it can be parsed and R vectors can be created very quickly. So data.table actually is extremely optimized for this use case, and it's able to read this data in under half a second. So that's going from like 120 seconds to a half a second. It's pretty impressive. Vroom is also pretty good for this use case, but it has to do a little bit more work than data.table because data.table can just index and parse the values directly into the vector, whereas vroom sort of has to do 2 passes. It has to parse the data first and then get all the values. So that's why this initial parsing is a little bit faster. The blue value here is a little bit faster than data.table, but once you do some of your, once you're doing the manipulations of your data, the total time ends up being slightly slower. There's also some interactions between the RCPP package and these Altrep vectors that are not quite optimal, that we can improve, and that's part of why you get this huge bar here. So this should actually, in an ideal world, this would be much smaller. But really what this bar is showing is that this is, and when you're doing this first sampling step, you're actually reading in all of the values at that step. And then that's why these are all basically the same, regardless of what package you're using. But this also illustrates the fact that like once you've read in all the values, you basically end up equivalent to using vroom without Altrep at all. So all characters is actually, so that was really sort of a worst case scenario for vroom. All characters is really a best case scenario. So we'll sort of see the opposite effect here. So again, read.delim is basically about as this. So this data set is again the same dimensions, 1 million by 25. The raw data is actually a little bit smaller than the double case. So if we go back, it was around a half gigabyte in size in total disk space. The all character data set's only around 400 megabytes, so it's slightly smaller. And read.delim takes around the same amount of time as it did in the all double case. However, all 3 of these, readr, vroom without Altrep, and data.table, are all much slower in parsing than when you're looking at the double case. So remember, when we were in the previous graph, the x-axis basically ended at 5 seconds. And here, even the best case data.table is taking around 40 seconds to parse this data. However, if we look at vroom with Altrep, it's able to do this in a third of a second, basically. So, and even after doing all of the manipulations, you end up being like 2 seconds or something like that. So this is like really a vast improvement over the other methods.
So
Yes.
you read it in as characters and convert it. Like, does that take more time?
What?
Convert it to numeric or whatever.
So you could. It probably would end up taking. I mean, you definitely could do that. I don't think it would be any faster than just reading it as numeric from the beginning. But yeah, you definitely could do that. That's sort of the benchmarking section of this. So, but there's some other features, some other nicety features in vroom as well. So the first of which is column selection. So often people will read in an entire data set. So here I'm reading in the entire taxi data set I've been talking about so far, and then passing that using to dplyr select and selecting a few different columns. So I'm selecting this medallion column, the date time, and any column that ends with about. And this is nice, but this is a nice syntax to have, but you're kind of wasting some time, right? Because you have to read in the entire data set, and then you're only selecting a certain number of the columns. So what vroom allows you to do is basically use the identical syntax with a column select argument. And this has the benefit of not reading in those extra columns. So it just skips those columns completely. You don't have to read in that data at all. And as you can see, the syntax is it uses this tidy select syntax, which you can use basically exactly the same syntax you would use using dplyr select. And you can also do things, so this is showing removing a single column. So if I don't want this hack license column, you can just use a minus sign in the column name. Or you can even rename columns by using an assignment like this. The next sort of nicety that vroom gets you to do, allows you to do, is reading multiple files. So if you have two different files that both have the exact same columns but are maybe runs from the same instrument on 2 different days, for instance, or you're getting like a CSV per day and you want to combine them all together into one data set. You can do that with these other packages, but it requires some boilerplate code to read in the files and then paste them all together. But vroom can actually do this for you by just passing in a vector of file paths directly into the vroom function. So here I'm passing in this example is showing passing in 2 files. And the other argument, ID, is actually, it creates a new column in your data, in the data frame that it returns, that includes the file path that each of the rows corresponds to. Because often the file paths actually contain data that you need, like the day that the CSV corresponds to, or the experiment, or things like that. So it's really useful to know exactly which file a particular row came from.
You mean like stacking from each other, right?
Yeah,
Oh.
yeah, exactly. So like in this taxi data set, there's 12 files, and that's actually what this benchmark is saying. There's 12 files that all have basically the same columns and just additional data from, I think they just split them up because the files are big. So this taxi data set is 12 1.5 gigabytes files, a total of 18.4 gigabytes, and 173 million rows. And it's 12 columns instead of 11 columns because we have this new column that contains the file path. And so here you can see it takes over 1,500 seconds for read.delim to read this file and combine it all together into one data set. And vroom is, with Altrep, is able to do it in 12.5 seconds. And then even after you're doing all the manipulations, I think it was less than 20 seconds to do all the manipulations on this 173 million row data set. So that's actually really cool. This is something that people really, struggle with sometimes that with using like readr or data table. It's not too much code to like paste these all together, but because there's no built-in solution for it, everyone does it in a slightly different way. So it's nice having something built in. So so far I've been talking about delimited files like CSVs and TSVs, but vroom also has a different parser for reading fixed width files. And these are files that rather than the columns being delimited by a character, they're delimited by the column location in the row. And these are very common for like US Census data, for instance, is often in this format. And so vroom has a very fast reader for this as well. So this is a real world data set, 1.5 gigabytes file with 500,000 rows and 156 columns. And vroom can read it in less than a second, 740 milliseconds. And this is another case where using the function read.fwf in base R is extremely slow. So for the same data set, it takes that function 17.8 minutes. So yeah, just use readr or vroom to read fixed width files. Yeah.
So the read CSV base R function, is that just the wrapper around read the
Yeah, exactly. Read.csv is, yes. Yeah. So so there's read.table, read.delim, and read.csv, and I think read.csv too. And they're all sort of built on each other. I don't remember which one is, it might be read.delim is the lowest, or possibly read.table. I don't remember which. But yeah, they're all sort of built on each other. So vroom also has a function vroom lines to read in lines lazily. So this doesn't do any. This is basically the same as calling vroom with a delimiter of a new line rather than like a tab or a comma. And this is really useful for like counting the lines in the file. So it's a very common thing to do is I want to know how many lines are in my file. And you can get this just using vroom lines and calling the length function on that vector. And it will get you the number of lines in the file. For this is the taxi file I've been talking about before. And vroom can count the number of lines in half a second. And you can see the timings for the other packages. And so this is a case where like R has a function read lines that's not that slow in this case. It takes around 20 seconds for it to read that, but still the vroom function is quite a bit faster. Vroom also has a writing function. So up to now I've been talking about reading, but vroom also has a multi-threaded writing function. And this lets you do what you would expect, write files. It also, just like if you've used the readr function, readr has the ability to, if you give the file name and a certain extension such as .gz, it will automatically pass or automatically write your file to a gzipped compressed file for you, so you don't have to like write a flat file and then compress it after the fact. It will sort of do it all for you. And vroom has the same capability. So this is now showing benchmarks of the two of all. This is showing write.delim, that's in base R, the writing function in readr, the fwrite function in data table, and the vroom write function in vroom. And you can see it's basically for doing most of the operations, it's basically equivalent to the writing function in data table. I mean, we can't really take advantage of Altrep in this case because the data has to be in your computer for you to write it, or in your memory for you to write it. So, but it's basically equivalent to the fwrite, but it also allows, because it takes advantage of, it can use R connections. It can do a few more things that fwrite can't really do because it can't take an R connection. So, so it can do things like write to the Z standard compression format, for instance. Oh, I should also mention that the gzip support that I'm showing here is only currently available in the devel version of data.table, but I think it should be coming to the CRAN version somewhat soon. Okay, so that's the presentation, but I wanted to show, since we have some time, I wanted to show sort of an interactive demo of using vroom. And yeah, so this is that same benchmark I was showing previously, and vroom actually ends up being like over a gigabyte per second, so it's 1,270 megabytes per second for this data set. So if we just, I don't know if that's big enough. Yeah, I'll make it a little bigger. It's too big. Okay. So actually, I'm going to restart that. Because apparently I have readr. Okay. Okay, so the first thing that's sort of new to vroom is this ability to read multiple files at once. So if I have, so this is that taxi trip fare data set I was talking about. I have four of the files here, and we can look at the file sizes. They vary a bit, but they're all about 1.5 gigabytes for a total of around 6 gigabytes. We can read them with one call to vroom. We just pass it in to the function, and then it's going to read the files. And these files aren't in the operating system cache, so the speed will be a little bit slower than it would be if I had like read them again, but they're still quite fast. And the other thing I'm showing is using the ID parameter to append this file path, which we can now look at. So you can once this is read in, it basically you interact with it just like you would any data set, any data frame. And all the values are just being pulled lazily under the hood. You don't have to do anything to interact with them. And we can see we have this path variable that has the file path. So yeah, and we can take the head and the tail, and they're basically both equivalently fast. It doesn't really matter where in the file we're reading from. We can quickly seek to it, and we can even randomly sample within the file without a problem. Because that file is kind of big, because that data set's sort of large, I'm going to close it and get rid of it for now. So I mentioned this ID argument. So now I'm using just the same data set, but instead of taking all the files, I think it takes like the first 1,000 rows of each file. Again, it's 4 files, and we can read them with one call, and then do the same thing. We can look at this path column to take the head and the tail. So if we look at the head, those are all in the first file. If we look at the tail, they're all in the 4th file, as you would expect. And if we make a table of all the values, you see each file. And I guess it was 1,000 total rows, including the header rows. So it ends up being 999 rows for each file. And then you can also change. So the value in this ID column, or this ID argument, is the name that you want the column to be. So if you don't like path as your name, you can call it something else like file path, and then df file path will be where it puts that file, or where it puts those file names. Okay. So I also mentioned that there's this call select argument. So this lets you do the same thing as dplyr select. So here I have dplyr select and a few columns. You can see I get that, so I get 6 columns back. And I can do the same thing with vroom, with this call select argument, and basically the same syntax, and we get the same columns back. And then if you wanted to do things like get rid of columns like the hack license, you can do that. Or you can even, I think this will work. Hold on, actually. I'm just gonna, I don't remember all the column names, so I'll figure out where the hack license is. Oh, this hack license. So if we want to get rid of hack license to like surcharge, I think we can do something like this. Oh, and you can't do it like that, but I think if you do this, then it won't work. Yeah. Sorry about the bad formatting. Yeah, so you can use this colon syntax to like do the range between column names, and then tell it that you don't want those columns by using a negative. And then you can also rename columns. So like let's say I don't like this medallion name, but I want it to be taxi instead, then you can do it like that. And then you see this first column is now taxi rather than medallion. So vroom also has an argument called .nameRepair, and this is called this because that's the same name as in the argument in the tibble package, as well as in read Excel. And what this argument lets you do is supply a function or a set of standard name repair routines. So what is name repair? Basically, if you have column names, they can, coming from a file, they can use basically any type of names whatsoever. And some of those names aren't really valid for our column names. So the name repair tells vroom how to massage those column names to make them valid columns. So you can do nothing. You can have minimal name repair, which basically means that it does just enough to make them valid R names and nothing else. And there's a few other cases. But you can also, there's some built-in cases, but you can also supply custom functions to this name repair argument. So toUpper is a function that built into R that will take any text value and convert it all to uppercase. So we can pass vroom the name repair argument, this toUpper function, and it will convert all of our column names to uppercase. So you can see all of our column names are now uppercase. And there's a very handy package for doing this name cleaning called janitor that has a bunch of built-in functions to convert columns to various naming conventions. So you use this make clean names function in the janitor package, and the second parameter is the type of name you want to create. So this is lower camel case names, which we can see what that looks like. I'm going to run this again. Lower camel case. So camel case is the syntax, the naming convention where you have a lowercase word and then the words are split by the case. So there's an uppercase letter and then the second word. So we have hack license and vendor ID and pickup date time. But there's also other ones built in like lower upper. So this is lowercase first word, uppercase second word. I don't really know why you want to do that, but it's there. And then my personal favorite is snake case. So that's the lowercase, the underscore separating the words. Kind of looks like a snake going up and down, which is why it's called that. Another function that I mentioned previously is vroom lines. So this uses this delayed parsing to quickly read in the lines. So often when people want to figure out the number of lines in a file, they'll use the command line terminal. So so if there's a the program WC on the Unix command line it stands for word count, but there's also, if you use the -l argument, it will count the number of lines, not just the number of words. So if we run that on our data, we get the number of lines here, and it took about 1.4 seconds. So the one's over here and the 0.44 ended up over there. And we can do the same thing in R using the system function. So the system lets you call a command line tool from R and then return the result to R. So we can do that, and then I'm using system time to just time how long this takes. And so that took 1.3 seconds, so basically the same as running it on the terminal. We can see we can do use vroom to do the same thing. And I guess I could use just system time as well to make it consistent. So I'm reading in the lines and then I'm printing the length of the lines as a separate call. And so that took 7.5 or 0.75 seconds in this case, and we got the same result. But the nice thing is that because this is an R object, you can actually do other things. You don't just have to get the length of the line. You have all those lines, and you can do things like look at the first 6 of them, or look at the last 6 of them, or sample lines inside as well. You can even like pass this to vroom and read those lines. So it's a little tricky. So you have to collapse them. And we're actually going to we'll take the first line, so to get the header, and then we'll take this sample of 5 lines, and then collapse with a new line character. And then we can run this, and it's interesting that it put NAs at the bottom, but yeah, then we can run this a couple of times, and so that's a nice way to sort of sample within your data without having to read. You don't even have to parse the entire data set in this case. You can just get the lines and then feed them into vroom. So I mentioned, I think briefly, that vroom has support for reading from R connections. And so you might not be familiar with what an R connection is. So R has this sort of low-level interface to it's an abstraction around files, basically, that lets you transform files on the go, I guess. Okay, so we have a few files here that are, so we have 2 files, I guess. We have one file that's just a regular CSV file, and one file that's a gzip CSV file. So you can tell that it's actually compressed because it's half the size. And we can read the gzip file, if I had spelled that correctly. We can read it just by passing it directly into vroom, and vroom, based on the file extension, the .gz at the end, detects that it's a gzip file, opens the proper R connection, and then parses the file. You can do the same thing manually. So there's a function gz file that creates a gzip file connection. And you can do this, so that's basically what vroom is doing under the hood, is it detects this extension and uses this gz file function and passes that to vroom. You can also read in remote files, so this is sort of doing the same thing. It's detecting this syntax, the HTTP or HTTPS syntax, and then creating the proper remote connection as well. So this is a file living on GitHub, and I can read it just by passing the URL into vroom. You can also use so-called pipe connections. So these are, if you're familiar with a Unix pipe, this essentially lets you run a program, a command line program, and then stream the results back to R. And we can use these in vroom, and this is really useful for calling command, for pre-filtering your data. So the grep, if you're familiar with the grep command line tool, it lets you search through a text file for strings. And you can use this in combination. So here I'm looking for any rows with the DIS word in them. And this corresponds to disputed claims in the taxi dataset. So I can stream that into vroom, and it will only return the data that that contains those words. And this is really useful when you have a lot of data and it maybe won't fit in your memory in R, but you know there's certain parts of that data that you're interested in. So I can do the same thing with all of the tripfare files. Just do the small ones. Well, maybe we'll try all of them. I don't think it takes that long. Oh, why did it? Interesting. Unknown devices option. Oh, I see. That's weird. Okay. So the .w is saying that telling grep that you want only the word DIS. So if it has white space or word boundary around it, and the .h is avoiding putting the file name by the. So when you pass grep on multiple files, by default it includes the file name in the results, so you can tell which file the rows came from. But in this case, I don't care what file they came from, and I just want the rows themselves. So you can see that actually ran over all of those tripfare files very quickly, because grep is quite fast itself in searching. So it's a way to take advantage of that quick speed from the grep program. And finally, so vroom write also has support for these R connections. So you can write normal files, but you can also write these gzip files, again, by just using the extension. It automatically opens the proper, it uses that gz file connection again. And then, but you can also use this pipe function when writing. So here I'm using the pigs command line tool, and this, if you're not familiar with this is a parallel implementation of gzip. So it allows, the one built into R is a single threaded, so it's fast, but it's not as fast as it could be. There's a parallel implementation that isn't built into R, but it does have a command line tool, and you can just pipe the results to that command line tool and take advantage of multiple cores. So this is actually can be much faster depending on the number of cores in your machine. But this also lets you take advantage of formats that aren't built into R, such as Z standard or other compression formats. So the Z standard format has a tool called ZSTD, and we can pipe directly into that and then and get the results. And then if we look at the file sizes of these results, we see the uncompressed file is 100 kilobytes. The gzip compressed is 44 kilobytes, and this Z standard is 41 kilobytes. Really, the benefit of Z standard is not necessarily increased compression over gzip, but it's much faster to compress. So it's really useful. You can compress the files almost as fast as you can write them as an uncompressed file.
Quick question.
Yes.
Looks like you're using some type of code format
For
to keep the code nice and neat.
somewhat. I mean, there's some built into our studio, right? If you go to code and reformat code, that will, if you just highlight the code, that will automatically format it in somewhat. And there's also so that is going to format it slightly different than I was. But there's also a package called styler that will do it as well. So I have it as an add-in. We can see what that will do. style selection. Yeah, so that will style it in a slightly different way. But yeah, I guess I styled this by hand.
Okay.
Yeah. But yeah, there's definitely options for styling your package, however. And then you can also, so that was all writing the files, but you can, and then read them, as I've shown before, you can read gzip files just by passing them in, but you can read the Z standard files with the Z standard. I'm gonna actually use unz standard, wait, and then you need standard out. And so I can read in these other formats, taking advantage of the command line tools. So these pipe connections are really powerful, and it's not just vroom that can read them. So if you're using data.table fread, it doesn't actually use pipe connections, but it does have this syntax where you just put the command directly in your. No, all my text seems to get gotten screwed up. But you just put the command directly into fread, and then it will run that command and parse the results. So that's useful, but I think it's actually more powerful to take advantage of these pipe connections. And they were introduced, they've been in R for a very long time. They were introduced way back in 2001 in R 1.2.0. So they've been available in R for a very long time, but not everyone's necessarily aware of them. And all of the built-in functions already work with them. You just pass in the pipe connection to those functions. So we can do the same thing I was just doing with vroom with like read.csv. Of piping in the results from grep, or write.csv doing the same thing with like gz file. So write.csv and read.csv won't automatically create this pipe connection for like gzip files like vroom will, but you can do it manually in this way. And then you can even take advantage of things like the multi-threaded compressor and other things. Or other archive formats like 7-zip. So there was a question on Twitter about, I'll just open it. If vroom is able to take something from a URL and then filter it using grep or other command line tools, and then passing it into vroom. And so the way that you can do this is using pipe connections. So in this example, which is unfortunately a little long because of the URL, you can download the file using the curl command line program, and the S here is just making the output silent, and the capital L is saying that you want to follow links. And then we have the URL, and we're passing that to grep. And then I only want, this is the MT cars data set, and I only want the Mercedes in this data set. So I can read it like this. And that works, so we see we get only Mercedes in this case. And that works well, but we don't have the column headers, which is kind of unfortunate. So how do we actually get those column headers? So one way would be to, rather than using grep, we can use Perl. If you're familiar with Perl, it's really useful for these one-liners like this. So we can say we want to print only the lines that have Mercedes in them, and that's the I is just saying this is a case-insensitive match, or this $period is the line number, and we say, so we were saying we only want if the line number is the first line, which is the header line. So this way we can get the actual data set that we want. So we have the header and we have only the Mercedes. And we can do this all in sort of one short command line call. And we can even do things like unzip the data before we pass it to Perl. So we're downloading the data with the curl program. We're using gzcat to unzip it and cat the output, and then passing that to Perl, which is then fed into R and read by vroom. So you can do pretty sophisticated things by combining all of these tools together. and taking advantage of these pipe connections and other connections. So as I mentioned, I'm the maintainer of the readr package. So sometimes people ask me if we have this new vroom package, how does that affect readr? And where is readr going to go? Is it going away? So right now, we're planning on sort of having them both live as separate things because we want to make sure that vroom is really stable, and we've sort of worked out all the bugs in the parsing. Eventually, I think that probably what's going to happen is vroom is going to be used as the backend to readr. So the readr parser is sort of going to have a few stages of deprecation, and eventually it might get removed, and then vroom will just become the default readr parser in the readr package, and everyone will just have faster parsing magically. So that was overview of the vroom package. It's on CRAN, so you can install it with install.packages vroom. There's a website at vroom.rlib.org. I made a YouTube video that sort of goes through a lot of the same things I talked about today. So you can get to that at bit.ly/vroom-youtube, YT. And then if you try the package and run into any issues, please open a bug on the issue page, github.com/rlib/vroom/issues. And it's really useful to have users try it out and report things. So I really encourage you to do so. Thanks, everybody. And does anyone else have questions? I know we were asking questions throughout, but yes, go ahead.
So when I've been reading the introduction to the package and stuff like that, and a lot of it's talked about like an interactive use, right? So you want to analyze large data sets interactively and stuff like that.
Right.
So whether it's just the Altrep framework in general or the vroom package, in a more like a production setting, like so, I guess you mentioned some of the trade-offs with how like the global memory pool works and stuff like that. If someone were to try to leverage vroom in, say, like the context of a Shiny application that you're trying to scale and stuff like that, is there anything that we would want to be aware of when trying to leverage vroom in non-interactive use cases?
So for the Shiny case, so in some respects, vroom is really useful for Shiny because often, so it depends how your Shiny app is set up, but often people are reading. So you can either, like, if you have a data set that the Shiny app is working off of, it's usually best to like do that up front before, like in your server code before each person is connecting to your application so that they don't have to wait for the data load. But vroom is actually really useful for that case because even if you are parsing when someone is first interacting, pulling up your Shiny application, the initial read is so fast that makes your website much more responsive than it would otherwise be. The only thing you'd have to watch out for is that it might make your intermediate operation slightly slower at first before, like the first initial read that the parsing, when it's reading the values, when you're doing your first manipulation. So that might be slightly slower than it would be if you're not doing this delayed reading. But I think overall, it should actually improve the user experience in most Shiny applications.
Cool. And so that, like, in a synchronous or asynchronous context?
Yeah, that shouldn't. I mean, that being synchronous or asynchronous shouldn't really matter. Like all of the threading that vroom is doing is divorced from ours, like multi-threaded, and the way that asynchronous applications work in Shiny. So there shouldn't be any interactions there, except that you might have like thread contention because vroom is using a bunch of threads, and like the asynchronous operations are using multiple threads as well. So that's the only thing you might run into. There's a environment variable you can set like how many threads vroom uses, so you can restrict that if needed. But yeah, that would be the thing to worry about.
Okay.
Anybody else? Yes.
Could you comment on, so this seems like it's so fast, how does it compare to using our data files when you save this?
Oh, okay, yeah. Yeah, so all of my comparisons were on like flat files. So yeah, how does it compare to like binary formats? So like an R data, so R like the RDS, like save RDS and load RDS are not that fast. So like vroom is probably a little bit faster than them actually. But there's some other packages like FST is a fast binary format, like and it actually no, so FST doesn't use Altrep, but there's a different package which I'm forgetting the name of. I want to say it's like QS or QR or something like that. QS maybe. Yeah, QS. So this package uses a very similar approach to vroom. It uses the Altrep as well, Altrep framework to delay the string parsing as well. So and it does a couple other things. It uses a very fast compression and decompression format. And this is really fast. This is like, so here they're comparing between save RDS and read RDS. And I think they have somewhere like the megabytes per second. I don't know where it is. Maybe they don't. But I mean, so this is reading what, like a 50 megabyte file. Save RDS and read RDS take 5 seconds to write it, and this is writing it in like 0.2 seconds or something. So it's actually, and these, so FST is the other one I talked about, and that's sort of on par. They're both very fast. I see, this is the compressed file size. So the other thing to keep in mind with save RDS and read RDS is by default they use, I think, gzip compression. And you can, if you're off, the main thing you're concerned about is speed. If you just turn off the compression, they're quite a bit faster. So so that would be, often people aren't aware that it does that it uses compression by default. So that's a way to get some speed. But yeah, those two packages, FST and QS, are both quite fast. If you need to do this binary serialization. Anybody else? All right. Well, thanks everyone for coming. Hopefully, I'll see you guys for the next meetup in October. It's October what? October 23rd. So hopefully I'll see you guys all there. Thanks.